In this video, we will talk about plotting scalar and vector fields. This is our overview slide, which I'll spend 3 or 4 minutes going over before I go through each topic in more detail and with more examples. First, we will talk about plotting scalar fields, and scalar fields are characterized by a single value at each location in time and space. We have this example of electric field potential. It produces a scalar value, and then later we will go ahead and plot the level curves over here. Next, we will talk about plotting vector fields, and vector fields have both magnitude and direction. So we have this electric field here, which takes an x and a y value, and it produces an x and a y value. So at each xy point, we get a vector. We talk about how vector fields then, we represent them by constructing lines which are tangent to the field vector at every point in space. And so we will do this example with using this electric field. But before we get into this, let's back up and talk about plotting scalar fields. For scalar fields, they are characterized by a single value at each location in time and space. So before we go into the physics examples, I chose the simple one so we could get a better feel for what's going on. But describe the graph of the quadratic function f of xy equals x squared plus y squared. Over here, I have a table of different values of x and y, and when I plug it into this function, I'll get f of x, or z, which is equal to x squared plus y squared. I'll start with x equals 1, so I come out here on the x-axis, y equals 0, so I don't need to move, and then z is equal to 1 at this point, so I get this point here. My next point, 0, 1, 1, x is 0, so I don't need to move any, y is equal to 1, and then z is equal to 1. So I have this point over, I have this point over here. So next I have 1 over square root of 2, 1 over square root of 2. So that's somewhere around 0.7 and 0.7, and I move up 1. So something about here. And again, because I take 0.7, 0.7, I draw my box. So this is it when z is equal to 0, but I move up 1 unit to get this point here. And if I keep drawing, what I'll get is sort of this circle. If I go to 2, 0, 2, again, x is equal to 2, so I'll go out 2 units, something over here, and then y is equal to 0, and then I need to go up 2 units, something maybe around here. And then at x equals 0, y equals 2, go up 2 units, maybe something around here. And then square root of 2, which is something like 1.4, I draw that square. So this, I'm going to say 1.4 somewhere around here. Draw 1.4 from y, so I'm at this height, but I need to go up 2 units, maybe around here. So I get this other kind of circle if I filled in these other points. But this is kind of, one, it's very slow if you're doing this by hand. So one suggestion, you can use Wolfram Alpha, which I will show you, but there's something else we used in vector calc. So let me show you level curves. The idea of a level curve is if you have a graph, let's just say of some mountain or something, say it's like in the real world. A level curve then will show you the paths that you can take along the mountain, and I'm just going to draw one in blue, where your elevation does not change. In other words, your height stays constant. Coming back and looking at our function, z equals x squared plus y squared, if we set this equal to constant, in other words, we want to look at the level curves where if we traverse the path of z, that our height will not change. And what you see is that our level curves are circles. And if our constant is c, the radius would be square root of c. Here I have our level curves for our quadratic, where z is held constant at 1, and that's a circle of radius 1, where z is equal to 4, and the level curves are circles of radius 2, and here z is equal to 9, circles of radius 3. And you can see if these are our level curves, as we go up, our circles get bigger, so our whole graph is kind of this paraboloid shape, a paraboloid of revolution. And so one of the plots we often did in vector calc, and also we will use in this chapter, is the plot of level curves. And here we have our 3 level curves with radius 1, 2, and 3. So the idea is when you have this set, this graph of level curves, you raise each of these curves up to the height of C above the XY plane. So you think of a circle kind of at height 1, a bigger circle at height 2, and then you can see as you get a circle, as the circles get bigger, you're going to raise them higher. So that's the idea of plotting a scalar field. Again, the idea of a scalar field is you take these x and y values, you get a single value for z, and you can plot them point by point. But a useful tool is to use level curves where you hold z constant and you determine what the level curves look like. Our example in the book is an electric field potential, this phi, produced by two parallel uniform line charges of plus or minus lambda naught coulombs per meter, located at x equals 1 and y equals 0, and at x equals -1 and y equals 0. So this is our phi is equal to lambda naught over 4 pi epsilon naught natural log of 1 plus x squared plus y squared over x minus 1 squared plus y squared. And we are going to start by noting that this is a scalar field, and it's a scalar field because phi takes an x and y value and then produces a single number. The next thing to notice is this is a three-dimensional plot because the two variables, the two input variables, x and y, will take 2 dimensions, and then the phi will be our z value, will be our third dimension. So much like our paraboloid of revolution in the previous example, this will be a three-dimensional plot. So much like the other example, I can actually go point by point. I have values of x here. I did this in Excel from -1 to 2, and values for y, I just held it for now constant at 0.5, and I plugged in the values and into this formula, and these are the values I get. So I can do this and go point by point, but that would take a long time and would be kind of miserable. So what I did is I plugged this into Wolfram Alpha, which is a program you can access online, wolframalpha.com. I told it I wanted to do plotting and graphics, and you can see the input I put in was exactly this phi. I ignored these constants. I just set that equal to 1 for this graph. And you can see I have this three-dimensional plot. And I also asked Wolfram Alpha, after it got the plot, to go ahead and show the level curves. So these dark lines in black, those are the level curves. And what you can see, these numbers over here that I plugged into Excel, that was when I held y at -1/2. So that's this y is equal to -1/2 here, 0 to 1/2. So it's kind of along this front face of this plane here is at y equals -1/2. And then I let the values go for x go between -1 and 2. So our x values are going to go between -1 and, well, this only goes to 1/2. But you can see along this face here, so hopefully these points should trace out this curve at -1. We're not quite at 0. 0 is at 0. But at -1, we're at -2. But you can see as we approach x's going towards 0, we eventually increase until we hit 0, which is over here. And then you can see we continually increase as we follow along here. But then somewhere around 1.5, I guess you can see we're starting to go downwards now, right? We start decreasing. So we do hit a maximum after we hit 1, and we start to decrease. This is kind of hard to see because this graph is kind of small, but if you blow it up, you can see that it sort of follows this line here. And the next thing I did is I really wanted to see these level curves because I really wanted to see that they looked like what they look like in the book. And if you look at this, this really does sort of look like the book, right? You've got circles spiraling down, circles spiraling up on the other side of 0. But in Wolfram Alpha, if you want to really match the curves, you can see, again, I said plotting graphs and curves. And I plotted several graphs, as many as I could before it said, Wolfram Alpha said I ran out of space. So here's one level curve. you can see I put in the natural log of x plus 1 squared plus y squared over x minus 1 squared plus y squared equals 1. So I just set this equal to 1, and that is my level curve. And here it's really small, but actually I'll blow this up so you can see it. So this in blue is my level curve when I set x equal to 1. And actually this was -1, not 1. But here you can see when I set it equal to 3, and that's this green curve here. Here you can see where I set Wolfram alpha equal to the level curve -2, which you can see is in purple over here. So in other words, this graph here that you see in your book is the level sets where we set this function phi equal to a constant. And then from these level curves, you get a sense of what the three-dimensional plot looks like. And again, here's the 3D plot. And you know, your book totally skipped going through the 3D plot, so maybe the level curves is all that you will need. A couple of more notes. The centers of the circle are located along the x-axis. You can see that. That's where x is equal to 0. Electric potential equals to 0 lies on the y-axis, which you can think of as a circle of infinite radius with its center at infinity. If the contours have evenly spaced constant values of phi, which mine do, I space them by whole units, the regions of highest line density show where the function is most rapidly varying with position. So here you have more density as opposed to out here. So although 1, 2, 3, yeah. So this one is 1, 2, and 3. This is evenly spaced. And this is evenly spaced too. But you can see that this area is not as dense, so it's not changing as fast. That's what we have for plotting scalar fields. So next we have plotting vector fields. And vector fields have both magnitude and direction. We are going to start with an example from vector calculus. So we have a vector field, and the thing about vector fields is it assigns to each point in its domain a vector rather than just a scalar value. So for example, if we have a vector function capital F that assigns the x equals 1, y equals 2, so it takes x equals 1, y equals 2 as an input and outputs the vector 4, 3, the way we represent this is attaching an arrow to each point, a vector. So what we do is we take this 4, 3 and we draw that vector. So this is vector 1, 2, 3, 4 in the x, 1, 2, 3 in the y, and then we will take this vector and we'll move it so that its tail is at the point 1, 2. So it's representing the fact at point 1, 2 we have a vector 4, 3. So this will be the representation of this vector here, this vector assignment. It assigns one at the point 1, 2, the vector 4, 3. And here I have an example of the function. So it takes an x and y, and it's equal to, its first coordinate will equal to x squared y, and its second coordinate will equal to 3x. So for example, if we plug in x equals 1, y equals 2, then this vector field will assign it the value, this is 1 squared times 2, 2, and then 3 times x is 3. So this will assign the point 1, 2, the vector 2, 3. So here I have the vector 2, 1, 2, 2, 3 is here, and I'm going to move it to the point 1, 2. So this is the representation of this problem here. I'm going to compare that to a scalar function, which I'll denote scalar with this lowercase f. Lowercase f takes an x and y value, and if it's a scalar function, it produces a single number. So I could have, for example, x squared y plus 3x. So when I plug in 1 and 2, I plug this in and I get 2 plus 3 is equal to 5. So this is the scalar function. It just produces a scalar, not a vector. So that's the difference between a scalar and a vector function. But you can see if we plotted all the vectors for all the points, our plot would just be one big blot. There'd be so many vectors all over the place. So there are different conventions to show an entire vector field. For this book, and in particular when we're looking at electric fields, we're going to show the vector field by constructing lines which are tangent to the field vector at every point in space. And by convention, the density of these field lines indicate the magnitude of the field, while the arrows show its directions. So here is actually a vector field, and I showed some of the vectors in the vector field, but the idea is if we come over here and kind of just take little tangent points, we'll get the sense that this vector field is kind of a swirly thing. I should be a little more careful. So here I have a tangent, here I have a tangent, here I have a tangent. This is all tangent because it's kind of straight. And then, yeah. And what you see is you see the rotational aspect of this vector field. For our example, we have the Cartesian coordinates of the electric field of the preceding example where we had two parallel uniform line charges located at x equals 1, y0, and -1, 0. The electric potential we had talked about as a scalar field was phi of lambda naught over 4 pi epsilon naught times natural log of x plus 1 squared plus y squared over x minus 1 squared plus y squared. So we can see that the electric field, and I wrote it here, the electric field takes an x and y value, and for its x coordinate will be x squared minus y squared minus 1 over x minus 1 squared plus y squared, x plus 1 squared plus y squared, and its y coordinate is 2xy, x minus 1 squared plus y squared times x plus 1 squared plus y squared. So your book has this notated as the x coordinate is e subscript x, and that's the negative partial derivative of phi with respect to x, and e subscript y, that's the y coordinate, is the negative partial derivative of phi with respect to y. And rather than trying to plot this vector field, we're going to use this here where we are going to construct lines which are tangent to the field. So I've kind of condensed this here. This was our electric potential, our original phi, our electric field. This is the x coordinate, this is the y coordinate. We have this comment that we're going to be constructing lines which are tangent to the field to kind of portray the vector field. And we're going to assume then the electric field lines for the electric field above is given by the equation y, which is a function of x. Since the field lines are tangent to the electric field, the tangent of the electric field then is the slope or rise over run. That is, the tangents are going to be e to the y over e to the x. So again, if this is our electric field and our field lines are tangent, then we want the slope of our y. And the slope is going to be rise over run or y over x. So we're going to have ey over ex, which ey over here over ex, fortunately the denominators cancel out, and we're left with 2xy over x squared minus y squared minus 1. Now we have dy dx, and for whatever reason I dropped the of x here, but this y is a function of x, otherwise it wouldn't make sense. Dy dx is equal to 2x, and for whatever reason I chose to highlight the fact that this y is dependent on x, over x squared minus y squared x minus 1. And so one thing about this of x, sometimes it gets dropped, sometimes I write it to highlight it. But anyway, this here, now we want the field lines tangent, and we know they satisfy this equation. This here is a differential equation. Your book notes that this can be integrated to give x squared plus y minus c squared equals 1 plus c squared, and this here is the form of a circle, right, with center at 0, c, and radius square root of 1 plus c squared. So between this statement and this statement, I think there's, at least another slide or two, but because your book didn't highlight it, for now I'm just going to say, one, that we can use y minus 2 as an integrating factor to solve this differential equation, and then once we solve it, there are other mostly algebraic manipulations then to get this circular form. So the details of that I'm going to save for the end of this video, so if you're not interested or don't need to see it, you can skip that easily. But if you are curious or you feel like you need to know, I have this at the very end. So I kind of condensed some things here. So we have our assumption, the electric field is given by dy dx is e to the y over e to the x is equal to 2xy over x squared minus y squared minus 1. And this can be integrated to give you x squared plus y minus c squared equals 1 plus c squared. And as we said, these plots then, for a given value of c, these are circles centered at 0c with radius square root of 1 plus c squared. Again, going to Wolfram alpha, here I plotted my, I let c equal to 1 here. Here I let c equal to 0.5, 0.25, 0, and then negative 0.5, negative 0.1. Also the equations are here. So this is the graph I got. Here I've zoomed in so you could get a better look. You can see on top where I have all the different equations where I set different values of c. Here I have c is equal to 0. Here I have c equals negative 0.5. And you can see I separated each equation because I wanted to plot several equations on the same graph. I separated each equation by these semicolons. And then here you can see this blue is where I set c equals to 1, so it's x squared plus y minus 1 squared equals 2. You can see the orange, that's where I set c equals to 0.5, so I have x squared plus y minus 0.5 squared equals 1.25. Over here in red, where it's centered at x equals 0, this is where c equals 0, so x squared plus y squared equals 1. And then over here I start, with the purple, I start having negative values. So first I have c equals negative 0.5, so x squared plus y plus 0.5 squared equals 1.25. Also, just because I wanted to see it, I did plot several positive values and then several negative values, just so I can kind of focus on just the positive, just the negative. So these are just this graph, but this is the negative half. This is the positive half of the graph. So to review what we've covered in this video, first we talked about plotting scalar fields, and scalar fields are characterized by a single number. So our example was this phi, the electric field potential phi, and it would take in values for x and y and produce a single number. This is a three-dimensional graph since our x and y is a plane, it's two-dimensional, and then our phi is the height above the plane. So it's a three-dimensional graph. And then we talked about holding phi equal to constant to get these level curves, which are drawn in black here. And I also went to Wolfram alpha and just plugged in the equation. Also, I let this part here, this constant equal to 1, just so I could see it easily or plot these more easily. And I would plot the graph of my log 1 plus x squared plus y squared over 1 minus x squared plus y squared, and I would set it equal to constants. I have it set it equal to constant 1, to 2, to 3, to negative 1, to negative 2, and I get my level curves. Plotting vector fields. So when you have a vector field, you take in two variables, x and y, and you get another vector. So you get a vector that has magnitude and direction. So here you have your x-coordinate, your y-coordinate, and for this book, we're going to draw vector fields by drawing lines which are tangent to the field vector at every point in space. And to do this, we note first, to get the tangent of our vector field, that's simply rise over run, or e to the y over e to the x, which fortunately things canceled out, and we got 2xy over x squared minus y squared minus 1. And this equation here, then, we can integrate to give x squared plus y minus c squared equals 1 plus c squared. So for every value of c, we see that this is a plot of a circle centered at 0c with a radius 1 plus square root of 1 plus c squared. I did say that there was a bit of calculation between these two statements, and so if you're interested, I am going to do that next, and if this is all that you need for your class, then you're welcome to end the video here. I cleared some things out, and the differential equation we're trying to solve is dy dx is equal to 2xy, and I put the of x to remind ourselves that y is a function of x, divided by x squared minus y squared minus 1. The first thing you may notice is this is nonlinear because of the x squared, the y squared. So because it's nonlinear, something like 80% of the techniques you learn in differential equation automatically doesn't apply, because most of them were linear equations, first order or second order, when you had the second derivative, differential equations, maybe Laplace. But anyway, but this is nonlinear. So where we're going to go from there are exact. We're going to hope we have an exact equation, because exact equations do not need to be linear. So if you're looking into your DiffEq book, look up the chapter on exact equations. I do have a video because I do have a playlist for differential equations course, and that's where I got this slide here, so I could review exact differential equations with you. And the first thing to know is the definition of an exact equation. So if you have an equation of this form where you have a function of x and y, and then another function, capital N of x and y multiplied by y prime equals 0, it's an exact equation if the partial derivative of m, that's the function just of x and y, partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. I'm going to use this example here. This is an exact equation to show you how this works. So if we have the equation 2x plus y squared, and y is a function of x, plus 2xy y prime, so rewritten just to highlight the fact that y is a function of x, 2x plus y squared of x, 2xy of x, times y prime of x equals 0. So here, m, again, well, I should start with n. N is whatever part of the function is multiplied by y prime. So here's y prime. So n of xy is equal to 2xy. The rest of it that's not multiplied by y prime is m. So m of xy is this stuff here, 2x plus y squared. So I'm going to take the partial derivative of m with respect to y, and I get 2y. The partial derivative of n with respect to x, and that gives me 2y. Since they are the same, right, then if they're equal, then that means this is an exact differential equation. And now I can use this method, which I've outlined right here, for solving the differential equation. And here it says that if it's an exact equation, then there's a function, this c, is this c, that satisfies the differential equation. And the proof is constructive, and I have more details on the proof and why it works in my differential equation video, but since this is more of a footnote, I'm not going to give you all that detail, but I will tell you that this is how you find C, which is our solution. So in our example then, the next step to do is to look at the integral of m of xy with respect to x, and that will equal to c plus some function of y. So integrating m with respect to x, so here's our m, 2x plus y squared dx. We integrate and we get x squared plus y squared x with respect to x. We're integrating with respect to x. Plus, we need to add a possible constant function of y, because remember, when we're integrating with respect to x, when we take the derivative of a function of y, this all goes to 0. So this is like the constant that we need to add on. So this is our proposed solution. It's going to be of the form x squared plus y squared x plus some constant function y, or some function of y. Now the second step is to find h of y. We're going to take the integral of n of xy minus dq dy, and q is the part of c that does not have h of y. For my example, I solved for hy over here, so I'm taking the integral of n of xy, which is over here at 2xy, minus the derivative of q, and again, q is this portion of our c. Just eliminate the hy, so d dy of c, which is x squared plus y squared x. And if you look at this, this is the integral of 2xy, derivative with respect to y, well, this goes to 0, and this is minus 2xy. So this is integral of 0, which simply equals a constant. So our function h of y is just equal to c, a constant, and our final solution is x squared plus y squared x plus c, and that will satisfy our original differential equation. So looking back at our electric field lines, we had this differential equation dy dx equals 2xy over x squared minus y squared minus 1. The first thing I'm going to do is multiply both sides of the equation by the denominator, so I get dy dx x squared minus y squared minus 1 equals 2xy. And then next I'm going to move the 2xy so I can set everything equal to 0. So I get x squared minus y squared minus 1 dy dx minus 2xy. So the n of xy, remember, that's what's multiplied by my dy dx, or my derivative of y. So n of xy is equal to x squared minus y squared minus 1. And when I take the derivative with respect to x, I get 2x. My m of xy is what is not multiplied, what's left, I guess. So that's my minus 2xy. When I take the derivative with respect to y, I get minus 2x. And you can see these two are not equal, and therefore this differential equation is not exact. So we need to look more at our differential equation review. That's this section here, integrating factors for equations that are not exact. You might remember the purpose of integrating factors. We also had these for linear differential equations, but the idea is maybe you have a small little function, which we'll call mu of xy, that you can multiply your entire equation by and then get something that is integratable. In this case, we're hoping that we can find the small mu of xy and get an exact equation. And just to clarify, when I say a small function, I mean a simple function, because the last thing you want to do is multiply it by something not simple, like a complex function mu, and then just make your differential equation even more complex and possibly harder to solve than the original equation. So what we are going to do is try to make mu a function of only x or a function of only y. To get a function of only x, we will consider m of y, the partial of m with respect to y, minus the partial of n with respect to x over n. Similarly, there's this form if you want a function of only y. For an example of finding this integrating factor, we'll consider this differential equation, 3xy plus y squared plus x squared plus xy times the derivative of y equals 0. In this case, our n is equal to our x squared plus xy. So n, partial derivative with respect to x, is going to be 2x plus y. So we have that here. Our m is our 3xy plus y squared. So our partial derivative of m with respect to y is 3x plus 2y. So plugging into this equation, my minus nx over n, I get x plus y over x squared plus xy, which simplifies to 1 over x. So now we're going to take du dx is equal to u times our my minus nx over n, so over x. So we can integrate both sides, and we get e raised to the 1 over x dx is equal to e natural log of x is equal to x, meaning u of x is equal to x. We return now to our electric field lines, which we found was not, this differential equation was not exact, but now we're going to consider an integrating factor. In our last example, we used my minus nx over n because we got a function of only x. In this case, that won't work, but we can get a function of only y. So just kind of reversing these roles, we're going to try nx minus my over m, and we see we get a function of only y. So now we can use the integrating factor e raised to the minus 2 over y dy will give us y to the minus 2. Next, we're going to multiply our entire equation by our integrating factor, y to the minus 2. And this is the new equation we get, so I'm just going to box it in blue. And if we look at our m of xy, that's equal to our minus 2x over y. Take the derivative with respect to y, that'll be 2x over y squared. We look at n of xy, we take the derivative with respect to x, and we see that's 2x over y squared. So now this equation is an exact equation, and we can apply our formulas from the exact equations. Now that we have this exact equation, the technique to solving the differential equation is we integrate m of x with respect to x, So here's our m of x with respect to x. So I pulled out the minus 1 over y because that's just constant when we're integrating with respect to x, and then we have the 2x. So we get minus 1 over y, x squared plus some function h of y. And we had to add the h of y since when we're taking the derivative or the integral with respect to x, any function of y is considered a constant. So this is like adding the constant at the end. We integrate n with respect to y. So where's n? Our x squared over y squared minus 1 minus y squared with respect to y is minus x squared over y minus y plus 1 over y plus a function h of x. I cleared out this space here so I could put my steps when we have an exact equation. So the first thing we want to do is integrate m of xy with respect to x. So integrating m of xy with respect to x. So where is my m of xy? It's over here. So with respect to x, so I pull out my minus 1 over y, since that's just a constant, integrating 2x with respect to x. So that's going to give me minus 1 over y times x squared plus some function of y, h of y. Now when we want to figure out what h of y is, we're going to integrate n of xy minus partial derivative of q with respect to y, and we're integrating with respect to y. And remember, q is the part of m that is not the constant function hy. So hy is the integral of n of xy. N of xy is equal to this x squared over y squared minus 1 over y squared. And we're going to subtract partial derivative with respect to y of q of xy. Q of xy is the part of is the part of m that's not h. So that's minus x squared over y. And now we integrate. So this becomes, we'll integrate with respect to y. So this becomes minus x squared over y. This becomes minus y. This here, we're going to take the derivative and then we integrate. So this is just going to become our plus x squared over y. So these two cancel out. So our h is going to be equal to, canceling these two out, our minus y plus 1 over y. So our solution is our m minus x squared over y plus h, which is minus y plus 1 over y. And this, plus c. So we'll say that's equal to c. So this is the solution to our differential equation over here. And I had to summarize everything, but this is where we're at right now. Now we're going to replace c by 2c for later convenience. So we're going to multiply this equation by y, so we get by minus y. So we get x squared minus 1 plus y squared equals 2cy. And then here we complete the square and we get our equation of the circle. So that was kind of a long detour, but just in case you wondered where we went from this equation to this equation, now you know. So that completes this video of plotting scalar and vector fields. Thank you for watching.